Hello my friends, this problem is a very much important for your examination point of view. I'll read the problem, carefully understand the given problem and how to solve this problem. You get it the idea step by step. Consider the bar shown in figure. An axial load P is equals to 60 into 10 to the power of 3 Newton is applied at its midpoint. Using elimination method and penalty method of handling boundary condition, determine the nodal displacement and reaction. This is the given bar element. Force has been applied at the mid node 60 kilonewton from a left hand side 150 mm length maintained and from right hand side corner 150 mm length has been maintained. That means L is equals to 300 mm. L1 and L2 is equals to 150 mm is given. Apart from this, area of cross section 250 mm square, Young's modulus 200 gigapascals. In this given problem, using elimination method as well as a penalty method, you wanted to find the displacement and reaction force. First, use the elimination method, find out the nodal displacement and reaction force. Then use the penalty method, find out the nodal displacement and reaction force. You will get a answer, maybe yes, remain same. Methods are different. Two methods we need to adopt. In a previous problem we have solved by using a penalty method separately and by using the elimination separately. So both method we need to adopt. First we will get all the displacement based on the elimination method and the reaction force we will get. Similarly, we will get a both the nodal displacement and reaction force by using the penalty method. We got the idea what is a given statement. Here one more difference is there. The difference between the previous problem and this problem is that he has kept a wall here, so that wall distance is providing the gap between the free corner of a bar element and surface of the wall, that is equals to 0.12 millimeter. The distance is maintained from the corner of the bar towards the wall surface is equals to 0.12 millimeter. That indicates after applying the load at mid of the bar element, this bar will get displaced from a node number 3 towards this wall only a fixed displacement, that is equals to 0.12 millimeter. After that, the displacement which will occurs in a element only in a node number 2, not in a node number 3. The restricted displacement is given in a problem. After this much displacement is occurs at a node number 3, there is no displacement at all in a node number 3. We are subtracting the effect of restricted wall displacement on a bar element from each and every forces has exerted at node number 1, node number 2 and node number 3. That is what we have here. Force F1 becomes F1 minus of stiffness of the element, which is at node number 1. It is exerting where? At node number 3. 1,3 value we have taken into A3. A3 means Q3. Similarly, force F2 becomes F2 minus of where it is exerting at node number 3 stiffness K23 into A3. F3 becomes F3 minus K33 into U3. These forces we have to take to solve the problem, not directly as a F1, F2, F3. The effect of restricted displacement in a given bar element should be considered on a applied force. That effect is occurring at the beginning on a force node number 1, node number 2 and node number 3 should be considered while solve the problem. Previous problem what we have solved, directly we have taken a force vector. After getting that idea about the restricted displacement in a bar element is given, that effect has considered in a applied force. We'll start solving the problem. What is the first task we'll do in a given problems? First we'll take the data, given data, applied force at mid node, that is equals to 16 to 10 to the power of 3 Newton, converted 60 kilonewton in terms of a Newton at mid node has been applied. Area of cross section 250 millimeter square. Young's modulus is given 200 gigapascals. The 200 gigapascal is converted to 10 to the power of 5 millimeter square. Then length of the element is given 300 mm. 150 plus 150 total length of the element, and he has given a maximum restricted displacement at the free end is equals to 0.12 mm. Then what he has asked to find out by using elimination method, determine the nodal displacement and reaction force. What we need to find out here, by using a elimination method, handling boundary condition, nodal displacement q is equals to question mark and reaction force is equals to question mark. Similarly, he has given in a problem penalty method, handling boundary condition, determine the nodal displacement and reaction force. What we are determining here, by using a penalty method, same nodal displacement and reaction force. Both the methods we are using. What is the first step of finite element method? As I have discussed in a previous video and in a previous problem, in any kind of a method you take down, either elimination method or penalty method, we have a first to four steps are common. In that first to four step, first we'll go and then we'll go with the elimination method and penalty method, applying the boundary condition to find out the given characteristics in a problem, that displacement vector and reaction supports at each node. Now modeling a single bar using a two element, each element having a two nodes as shown in figure. We have a given problem as a single element. This is in a single element. From the single element we'll make a two elements. How we are making? Based on the force representation. We'll take a two elements based on the force representation. Force here at the midpoint, from this point to this point I'll say as a 1. From the fixed point towards the applied load at the midpoint, element number 1. From applied load towards the restricted displacement, I'll take a element number 2. Single element becomes two elements. Element we are representing terms of a finite element model towards right direction bar has represented. We know that L1 is equals to L by 2, L2 is equals to L by 2. Then L1, L2 is equals to L by 2 is equals to 300 divided by 2, 150 mm L1, L2. Comparing the figure FE model, we have the data is this one. P is equals to F2 is equals to 60 into 10 to the power of 3 Newton. F1, F2 is equals to 0. E is equals to E2 is equals to 200 gigapascal, 2 into 10 to the power of 5 Newton per millimeter square, where A1, A2 equals to 250 millimeter square, L1, L2 is equals to 150 mm. All why we are taking as a common here it is common, here it is common. We have a only single bar element. Assume it is two element. Assumption, due to assumptions we have taken. That means the area is not get changed. It remains same. Just it has two elements based on the finite element process. Discretizing a continuum body in terms of a sub numbers of element based on the geometry, based on the applied force, or based on the characteristics of the given problem. We are discretizing, right? The first step of FEM is discretization. Just we have discretized a given model based on the applied force at midpoint. Next step finite element method is finding the elemental stiffness matrix. What we are finding the elemental stiffness matrix by using a generalized equation which we have derived in a beginning class. KE is equals to AEEE divided by LE 1 minus 1 minus 1 1. We how many elements we have considered? Two elements, 1 and 2. Consider a element number 1, E is equals to 1. Then this equation is yields to K1 A1 E1 divided by L1 1 minus 1 minus 1 1. Substitute the value of area of cross section A1 E1 L1. We know here A1 is equals to 250 mm square, E1 is equals to 2 into 10 to the power of 5 Newton per millimeter square. Length L1 is equals to 150 mm. Calculate this value. this value is equals to 3.33 into 10 to the power of 5 as it is 1 minus 1 minus 1 1. Now take 10 to the power of 5 common, multiply this 3.33 inside the matrix, will have a 3.33 minus 3.33 minus 3.33 3.33. After getting this elemental stiffness matrix for element number 1, we have the idea to give the row name and column name with respect to the element is present between the nodes. The characteristics of the node is equals to the characteristics of a row and column of the matrix. So we have that idea. The element number 1 is lies between node number 1 and 2. First row first column name as a 1 and 1. So then second row second column name is given as a 2 and 2, right? After giving that names of the rows and column, we need to go for finding the second elemental stiffness matrix. So consider element number 2, E is equals to 2. Generalized equation becomes a K2 E2 divided by L2 1 minus 1 minus 1 1. As similar to that previous bar element, we have the same dimensions and same length and material property. Why we are taking a single element in terms of a two element after discretizing by using a finite element method. A2 is equals to 250, E2 is equals to 2 into 10 to the power of 5 Newton per millimeter square, L2 is equals to 150. The calculated value which is equals to 3.33 into 10 to the power of 5, and then multiply inside 10 to the power of 5, take out common, this becomes a 3.33 minus 3.33 minus 3.33 3.33. So second elemental stiffness matrix we got. After getting the second elemental stiffness matrix, element is lies between the two nodes. From node number 2 it will get start and ends at node number 3. Now give it the name of rows and columns. First row first column name I will give as a 2, second row second column name I will give as a 3. Why? The element is lies between node number 2 and 3. The element will get start from node number 2, means the characteristics of first row first column name is equals to 2 and 2. The second row second column name of the matrix characteristics depends upon the node number 3 of element 3 and 3. We got this idea. After getting that a global stiffness matrix, we'll find the global stiffness matrix. We have the two elements K1 and K2. We found add it to both the K1 and K2 value. We know that how to add this K1 and K2 value. Consider two elements. Each element has a two nodes which has a connectivity with that each and every element. How many nodes are present in a given element? And after converting a FE model, 3 nodes, 1 2 and 3. 3 node into 1 degrees of freedom at each node. We have a Q1 at node number 1, Q2 at node number 2, Q3 at node number 3. Each node has 1 degrees of freedom, right? That is equals to 3. Then matrix is 3 cross 3 matrix we will get. I write here 3 cross 3 matrix 1 2 3 1 2 3. So then I will consider a row number 1. I will found in a both matrix we have a row number 1 here. To get a first row first column, first row second column, first row third column. So row number 1 is here, but row number 1 is not here in the matrix. It will start from node number 2 and ends at node number 3. So that means the first row first column name is this one, first row first column 3.33. First row second column name, we have first row second column name minus 3.33. First row third column we don't have, that is equals to 0. Similarly I go with that next bit, second row first column, second row second column, second row third column. Where is the second rows are there? We have in the first matrix as well as in a second matrix, second row. So now we'll go with the second row first column. What is the second row first column? We have here minus 3.33, have as it is written. Anywhere here in the matrix? No. So plus 0. Then second row second column this value, second row second column we have this one, second row second column. Similarly second row second column is also available in the second matrix. That means 3.33 plus 3.33 we have here. So this value 3.33 plus 3.33. Why? We have second row second column, second row second column. So after that, second row, second column, second row, third column, second row, third column we have here, but we don't have any value here. 0 plus minus 3.33 becomes minus 3.33, right? So after getting this all values of a second row, then we'll come to the third row. Third row we don't have any values here in the first matrix. Third row we have in the second matrix. Third row first column is equals to 0, we have taken here. Third row second column minus 3.33, third row third column 3.33. We know this complete concept of assembling the elemental stiffness matrix, getting the global stiffness matrix from the elemental stiffness matrix. 6.66, rest of the all values are remains same as it is. I have copied, only this center value will get changed. Now after getting that global stiffness matrix, we need to get a global displacement vector. We have a 3 nodes. At each node we have a displacement, one displacement at node number 1 q1, at node number 2 q2, and at node number 3 q3, right? Till this step what I have stated, it is remain same for both method. Now take a first elimination method and then penalty method. I'll use the elimination method handling boundary condition. We found this all elemental stiffness matrix, then we'll get a equilibrium equation, right? This equilibrium equation. Before getting this equilibrium equation, we need to get this, right? First we need to get the characteristics of the elimination method, then we'll apply the boundary condition. Using the elimination method of boundary condition, the global force vector is given by, in a given problem, initial or maximum limiting displacement is given, that is the gap between node number 3 and wall support at the right hand side end with a 0.12 millimeter. Thus the force at node number 3 F3 is equals to 0. Load vector can be written with the effect of wall support is given by, as I have discussed in the beginning of this problem. See here, force vector F is equals to F1, it is applied force, F2 is applied force, F3 is applied force. This is a wall effect. Wall effect, where is the wall is there? At node number 3, right? At node number 3 means K13, K23, K33 we are taking. Concept is very much important while we'll consider a wall effect on a applied force in a given problem, right? So what is this K13, K23 and K33? These all three values we'll find now. So here from the stiffness matrix is equals to 0. Now we'll get a K23. So K23, so K23 is this one, right? Second row, third column. This indicates. So third row, third column, K33. Third row, third column is this one, last value, into 10 to the power 5 we have taken. So these values are there, K13, K23, K33, we have these values, and A3 is equals to Q3 is given fixed value 0.12 millimeter. Maximum displacement at node number 3, Q3 is equals to A3 is equals to 0.12 millimeter. Now we'll represent the fourth step. Now fourth step will come, equilibrium condition. We'll take the stiffness matrix as it is, this stiffness matrix and displacement vector, but force vector will take this one, right? So now the equilibrium equation, KQ is equals to F K matrix and Q vector force vector with a wall effect. Now we know that applying the boundary condition elimination method, by using the elimination method, Q1 is equals to 0, Q3 is equals to 0.12, but it is also fixed. Known numbers of displacement is also said to be as a fixed displacement. When we'll see the fixed numbers of displacement, we'll say in elimination method we need to eliminate that fixed displacement respective row sign column. Corresponding row number and corresponding column number we need to find and search in a matrix. Then we will eliminating in a equilibrium equation to reduce the numbers of equations. Now we will see a q1 is equals to 0, q3 is equals to 0.13. Node number 1 is a fixed, q1 is equals to 0, but q3 has a restricted amount of displacement, that is also considered as a fixed node. Eliminating first row first column, also third row third column, corresponding rows and columns with respect to the known boundary condition of a given problem. Matrix what we have here in a 3 cross 3 matrix, so q1 is a fixed is equals to 0, q2 is approximately fixed. So we have this one with respect to this condition. First row first column is eliminated, third row third column is eliminated. You can see this box is not eliminated. 3 cross 3 matrix becomes a 1 cross 1 matrix after eliminating the rows and column, after applying the boundary condition. I will take 6.66 into 10 to the power of 5 into q is equals to f2 minus k23 a3. So we know we need to find out this unknown value. We know the value of the f2 is applied load 60 into 10 to the power of 3 Newton, and a3 is equals to q3.12 millimeter, and we have a k23 from the matrix. K23 is equals to minus 0.33 into 10 to the power of 5. It has been not taken here, but here it has taken, correct. So now we have this one. After substituting all these values in this equation, we'll get a value of the q2. The q2 value is equals to 0.1500909 millimeter. Represent displacement vector. Q is equals to q1 q2 q3. q1 is equals to 0, q2 is equals to 0.15009, q3 is equals to given 0.12. It is the answer for a displacement vector by using a elimination method. Similarly, next step we need to find out the supporting reaction. What is the supporting reaction? We need to find the reaction force at the fixed point. Okay, we know that the equation to find out the reaction force at the fixed point by using elimination method, R is equals to kq minus f. So we have all these values. Stiffness matrix, substitute that stiffness matrix. We know that displacement just now we have found, and we know that force here a very much important. Take a care of this, substituting the value of the force while we'll find the reaction force. The reaction force will not affect to the wall. So reaction force is occurring on the fixed point. That means we need to consider this only for finding the displacement, but finding the reaction force will not consider any effect of wall here. Direct given value 0, 6 into 10 to the power of 4, 0. F1, F2, F3 direct values we need to take. After this we will resolve these matrices. 3 cross 3 matrix is multiplied with the 3 cross 1 matrix becomes 3 cross 1. So we have first we'll take this one, then we'll take as it is here. Finally we'll subtract this value with this. So now I'll consider this, resolve this, multiply with row with respect to column. 3.33 into 0 plus minus 3.33 into 0.15009 plus 0 into 0.12. First row column has been completed, and then second row you take down. Minus 3.33 into 0 plus 6.66 into 0.15009 plus of minus 3.33 into 0.12. Second row first column is over. Third row 0 into 0 plus minus 0.33 into 0.15009 plus 3.33 into 0.12. So then find out this sum of this value, sum of this value, sum of this value will sum of that value is equals to, this value is equals to minus 0.499797. 10 to the power of 5 I have taken common as it is, and then similarly second row equals to this value approximately equals to zero point 0.6 we have taken, and then third value we have minus 0.100197. Then after resolving this we'll subtract these values with the matrix. So now what we will get here, we'll get here, I'll multiply this 10 to the power of 5 inside the matrix. This will equals to 49979.97 minus we have. So this approximately equals to 0.6 we have taken. When we'll multiply 10 to the power of 5, it becomes 6 into 10 to the power of 4. Similarly here, when we'll multiply this value for this minus 10019.97. Now we'll subtract this value, this minus 0, this minus this, 10 to the power of 6 into 10 to the power of 4 minus 6 into 10 to the power of 4, that is equals to 0, this minus this. So we have a reaction force at node number 1 this much, and reaction force at node number 2 is equals to 0. Reaction force at node number 3 is equals to this. After using elimination method, we found displacement at each node reaction force. Similarly, I will use a second method using a penalty method of handling boundary condition. We need to find displacement and a reaction force. Now step number 4, equilibrium condition is remains same. I'll take as we have derived here that equilibrium equation, as I have told, step number 4 will remain same, K matrix, Q matrix, and that force vector F. We know that we are adding the K11 value, K33 value, F1, F3. On this marked portion we'll apply the penalty value C. So now after the fourth step, equilibrium equation, we'll get that equilibrium equation K into Q into F matrix. Then we'll need to find penalty value, means we need to apply the boundary condition. We are handling the boundary condition by using a penalty method, that is Q1 and Q2 is equals to 0. We have assumed in a elimination method Q2 is approximately equals to 0 we have assumed, but here no assumptions. What they have given same characteristics will take. The element is fixed at this node, and force at mid. Then at node number 3 restricted displacement is given here, 0.12 mm. So this restricted value that will not be get affected here will take only the addition of a penalty value. We need to find in a penalty method which is the largest value is available in a K matrix. The K matrix is this one. In this K matrix already I have highlighted here a largest value in a matrix 6.6 into 10 to the power of 5, that is K22 is equals to 6.66 into 10 to the power of 5 Newton per millimeter. That is a maximum value, largest value, that is equals to max Kij. So this value will substitute in this equation. K max is equals to Kij into 10 to the power of 4. I have substituted here, so we can get the penalty value. The K max value is multiplied with the 10 to the power of 4. Then this value is equals to 66600 into 10 to the power of 5 Newton millimeter, the penalty value of a given problem. So the penalty value, after getting that penalty value, we need to add to the K11 and K33 value, because it is assumed as a fixed support are located at node number 1 and 3. So what we have after substituting here, this one K11 becomes K11, we have 3.33 plus 66600 into 10 to the power of 5 plus 3.33 into 10 to the power of 5. When we'll add this 10 to the power of 5, we'll take common, then here 66600 plus 3.33, when we'll add here, so this will be equals to 3.33. Total value of this is equals to 10 to the power 5 66603.33. So then that value here we have added to a K11 and K33, 10 to the power 5 we have taken out. So stiffness matrix based on the elimination method we got. After that we need to get a force vector is get changed. Force vector means in a penalty method in the last problem I have stated, and in a formula list also have given first force added the penalty value, and last nth force is added the penalty value. Intermediate forces will be remain same. So we have three forces, F1, F2 and F3. First force is F1, second force is F2, third last force is F3. That means we need to add for first force and last force is F3. We need to add the penalty value for the first force number 1 and force number 3. We will get a global force vector based on the penalty boundary conditions. That is F1 becomes F1 plus CA1. F1 is a given data. C has a calculated penalty value. A1 is also a given data. A1 is equals to Q1 is equals to 0. F1 is equals to 0 is given in a problem. So then similarly F2 is equals to 16 to 10 power of 3 Newton, and F3 is equals to 0. C value we known, we have calculated. A3 means Q3 given restricted value of given problem, that is a bar element is this one. The restricted value from this point to this is equals to Q3.12 value is given. So this one Q3, so we need to multiply Q3 value into C plus 0. In the previous problem all these values is equals to 0 we got, but here restricted value is given. That is the reason force 3 also will get after applying the boundary condition, this one, right? So first force all the values are 0. 0 plus 66600 into 10 to the power of 5 into 0. A1 is equals to 0. F is equals to 0. A0 is multiplied with the C value is equals to 0. We got this 0. And then we have same value F2, 16 to 10 to the power of 3 we have taken. Then we have F3. F3 is equals to 0 Newton. And then C value we have 66600 into 10 to the power of 5 we have taken this value, and then into 0.12. So this value is equals to 7992 into 10 to the power of 5 Newton. So we have this global force vector after applying the penalty value. Then we'll take a global equilibrium equation K matrix, F matrix, Q is remains same. So we have this equation, equilibrium condition after applying the penalty value is this one. Penalty values we have applied, and then this force we got instead of 0. Now press in your calculator, no need to convert that in terms of a matrix, matrix in terms of a equations. Reduce the time to write up in your external examination. Use the calculator directly. Press mod button in your calculator 3 times equations will come. Press number 1, select it that equations 3 unknowns, so we have 2 and 3. In that 3 unknowns you select it, then and enter the a1 value is this one, then b1 value is this one, c1 value 0, d1 value 0, equals you put it after entering the all values. So don't leave it this 10 to the power of 5. When you'll enter this a1, b1 and c1 value, multiply with this all values. When you'll enter the 10 to the power of 5 value, multiply it into that values. So similarly, after that again another equation is generated in your calculator, a2, b2, c2, d2, this one a2, b2, c2. This multiply with the 10 to the power of 5 equals button, enter it this with the 10 to the power of 5 equals button, enter it this value with the 10 to the power of 5 equals button, then enter this 60 into 10 to the power of 3 d2 value equals, then again similarly enter it with a3, b3, c3, d3, a3, b3, c3, d3 value, multiply with this 10 to the power of 5, multiply with the 10 to the power of 5, multiply with the 10 to the power of 5, don't leave it this one, d3 is equals to this value. Press it equals button, you will get the value of x which is equals to q1, value of y which is equals to q2, value of z which is equals to q3, value of x q1, value of y q2, value of z q3. So we got the value of this, these are the values, but when you'll compare to the previous problem, you will get the same answer. At q3 we got the 0.15 millimeter. Addition to that, more accuracy will get in a penalty method. This are the two values are more accurate, we got the result. It is also remain same, approximately equals to given value 0.12 restricted force here wall, and this is the corner, we have 0.12 bar element is given, right? So this is the same value what we have is this one, right? Approximately equals. So when we'll compare this value with the previous method, you can see here it remains same. See this, both values we found in the both method, same value we got the results. Okay, so we have this one penalty method, q value we found, the q vector we have represented in terms of a millimeter. Then we have a supporting reaction. We know that how we need to find out the supporting reaction. We know that from figure fixed at node number 3 and node number 1. So reaction force seen at node number 1 and 3. We have this figure, just I'll bring that again figure to cross verify. You can see here and you can check out. So here we have fixed here and approximately fixed. This we'll assume as after displacing a 0.12, we'll assume there is no displacement. That is the reason the reaction force is also. So we have Ri is equals to minus Cqi Ai, general equation. You remember this equation. After that, take it as a node number 1, I is equals to 1. So then we'll get a R1 minus C1 Q1 A1 is equals to 0. Q1 we have calculated here, the calculated value just now we got that value. Q1 is equals to this one, right? A1 is equals to given value, A1 is equals to 0. Then all the values you substitute these values, we have the reaction at this node number 1, 49979.00 Newton. So you can check out at this value with the help of penalty method. Same value we have found here with the help of elimination method. See this one at node number 1. Similarly at node number 2, now itself you remember this value, 10,019, approximately this value we need to get, right? I is equals to 3, r is equals to r3 is equals to minus c q3 a3. Penalty value we found 66600 into 10 to the power of 5 Newton per millimeter, and q value we found this value 0.1200015047. So this much decimals why we have taken, this is the reason he has given this 0.12. This is the difference what we have. So make this calculated value, we have a calculated value, we need to write all these decimals is very much important. Now you got the idea why I have written this all decimals, right? So now this is the calculated value, this one is a given value at node number 3, the displacements. Now I'll substitute this value here and substitute I value this one, substitute this all values in this equation number 3. We get all the values, calculate that. Final answer is equals to 10,019 we got in a elimination method. Here 10,016.49 Newton. It is approximately equals, both are equals. So either you will use a penalty method, either you will use a elimination method. Both method, if you utilize the same value, you will get same answer. You will get more accurate result. You will get in a penalty method at the displacement part, right? Both combination. That is the reason I have taken to define the difference between elimination method and penalty method. Now you have the idea of this. I have completed a part B of module number 2 as per the curriculum of VTU, and then part C of module number 2 I'll take in the next video, that is a trusses, analysis of trusses. What is meant by a truss? Truss is an element which is a combination of more than one bar element or link element which has a relative displacement. Trusses means the truss element is an element which is a combination of more than one bar element or a more than one link element has a relative displacement along the Cartesian configuration or global coordinate system or local coordinate system or a natural coordinate system. So the element which has a relative displacement due to the application of a load at any node in a interlinked bar element, such element is said to be as a truss element. So in the next video we'll get the idea of about the stiffness matrix of a truss element and definition of the truss element. Thank you for listening my lecture.